Are those problems on the practice tests? They just say can we do problems? Okay. Sweet. Yeah, I think since this class is behind, he's not going to do practice tests here. Also, the other TA is not going to be here today, so which is fine.
I'm sure she didn't come out.
Can you go ahead and switch over to the other camera?
Well, she would be able to do something.
Next to it. There you go.
Okay. We have talk. Okay, let's do some homework problems on chapter. Which chapter is this? If you don't tell me the chapter, I probably cannot look at the right problems.
That returned on your order 2014 Kia Sedona to a or John Bingham or a Carol.
Okay. So I guess either chapter. So which chapter is due tomorrow? Tomorrow we have a homework assignment due tomorrow. 22. Okay, let's try 22. Yes, you is the right thing. Should we? Oh, not everybody has a laptop in front, so we have to project. And have to see also what is happening. Board. So let's do problem number 13 in the homework assignment on chapter 22. And that problem looks like this. You want to make a solenoid with inductance of 2.2 millihenry. It has to have a cross-sectional area that has certain value and a length that has certain value. How many turns you have to, how many turns in this coil, in this solenoid? Well, there is a formula that we derived at some point describing the inductance of a solenoid in terms of its size and number of turns. And unfortunately, I don't remember that formula, so we probably have to derive it again. So the formula for the inductance of a solenoid includes number of turns per unit length squared, includes the length of the solenoid. Well, yeah, the length of the solenoid is included in lowercase. So it includes something like this: the length of the solenoid. What else does it? Cross-sectional area is included, but I don't remember exactly if there are some other coefficients. So let's derive that formula. So problem number 13, let's derive this formula. So you have a solenoid. And let's say that in this solenoid, the current that is flowing is current I. Let's say that the number of turns is capital N. Let's say that this length of the solenoid is lowercase l. And let's say that the cross-sectional area here of the circle is area A. So in order to derive the formula for inductance of a solenoid as a function of its size and number of turns, first figure out the magnetic field inside the solenoid. And if you remember from previous chapters, chapter 21, I guess, the magnetic field inside the solenoid is mu naught times the current times the number of turns per unit length. So lowercase n is capital N, the total number of turns, divided by the length of the solenoid L. So this is the magnetic field inside a solenoid. Well, if this is the magnetic field, the magnetic flux that goes through a single turn is going to be, so this magnetic field, of course, is this way, parallel to the axis of the solenoid, either in this direction or in opposite direction, depending upon which direction the current is flowing. But the magnetic flux through a single turn of the solenoid is going to be the area of that turn multiplied by the magnetic field. The angle between the magnetic field and the normal to the area is 0. Cosine of 0 is 1, so I'm not writing it. The total magnetic flux in this solenoid is going to be proportional to the number of turns in the solenoid, right? Each turn has A times B, and N turns give you a total of magnetic flux of this expression. And now recall what was our definition for inductance. So we said that the total magnetic flux is proportional to the current, and the coefficient of proportionality we called inductance of the solenoid, inductance L, capital L. In other words, the inductance is defined as total magnetic flux. Well, let me write it. Well, I messed up the notations. So just keep, since I introduced total magnetic flux, N is already here, so I don't need to write it anymore. So the total magnetic flux divided by the current is going to be your inductance. In other words, the inductance of my solenoid is going to be the number of turns times the area, cross-sectional area, times the magnetic field divided by the current. But the magnetic field is mu naught times I times N. So I have N times A times mu naught times current times lowercase n, all of this divided by current. So the current cancels out. The current cancels out, and now we're ready to, well, we have the formula. So the formula for the moment looks like this. The inductance of a solenoid is equal to number of turns times cross-sectional area times magnetic permeability of vacuum mu naught times the number of turns per unit length, and that's it. So just rewrite the number of turns per unit length, this capital lowercase n, as n divided by L. And this is going to give you the formula in a form that is needed. In other words, you're going to get that the inductance of a solenoid is mu naught times area times number of turns squared, all of this divided by the length of the solenoid. So in our case, we're given the inductance capital L, cross-sectional area is given in SI units, the length is given in SI units, the number of turns squared is going to be inductance times the length divided by mu naught, and the area. So this is number of turns squared. You have to take square root of it. And round this number to an integer, I guess, if you want to have an integer number of turns. I don't know how WebAssign wants it, in integer or fractional number. Try either way. So again, the formula for inductance of a solenoid with n turns, it is either written this way, but in the textbook, I think they write it as mu naught times area times lowercase n squared times the length L. So in the textbook, they write it in this form. It is in one of the examples in the chapter. Okay, any questions and remarks? So if you are able to follow at home independently this problem, you're going to have a good idea what inductance is, what Faraday's law of inductance is. So it is a good exercise to go over this question independently. Again, a similar calculation is done in example in the textbook. Any remarks and questions at this point? Feel free to comment. Okay, let's go to problem number 14 in the homework assignment. Yeah, mutual inductance is actually what is used in metal detectors. Those metal detectors that are at the entrance of every federal or state building, and also the metal detectors that people go around beaches and find. I don't know what they find, but they find stuff. So mutual inductance can be used, and it is used for a metal detector. This is the standard. Typical setup uses two large coils that are parallel to each other and have a common axis. Because of mutual induction, the AC generator connected to the primary coil causes EMF that has certain value in the secondary coil. When someone without metal object walks through the coil, mutual inductance and thus the induced EMF doesn't change much, because people, the magnetic properties of water and our tissues are pretty close to the magnetic properties of air or vacuum. But when a person that carries metal objects have different magnetic properties, in a sense that even though they are not magnetic, they, especially iron, brings the magnetic field lines in the iron itself. So the iron kind of attracts magnetic field lines, and therefore it changes the magnetic field substantially. The magnetic properties of the space between the two coils, the primary and the secondary coil, the magnetic properties change substantially when you have some iron in the space between them. Or other metals also would do, but the best is iron, nickel, cobalt, materials that have ferromagnetic properties are the best. So this is why handguns that are made of ceramic material or even plastic nowadays cannot be detected with metal detectors. And I don't know if they're illegal, but they're definitely frowned upon. So on the internet, you probably can find anything. So person walking, carrying handgun, walks, and the mutual inductance changes, increases usually. The change of EMF can be used to trigger an alarm. The mutual inductance increases by a factor of 2. Find the value of the induced EMF. So here we need a definition for mutual inductance. And the definition for mutual inductance, again, is similar to the, so let me write it here. So here is one coil, secondary coil, let's say, number of turns and secondary. And here is the primary coil with number of turns and primary. And the primary coil is energized with AC voltage, AC variable voltage. So this is N primary. So it is clear that the total magnetic flux in the secondary, which is, let's write it like this, number of turns in the secondary times the magnetic flux through a single turn in the secondary, is going to be proportional to the current in the primary. So the current, let's say in the primary, it is a current that is variable in direction, so it goes back and forth, but it has some RMS value, and we call it I primary RMS value. So it is proportional to the primary. The coefficient of proportionality we call coefficient of mutual inductance. So they say that if the mutual inductance increases by a factor of 2, find the new value of the induced voltage. Well, if you remember the induced voltage, let me see our definitions, because so the induced voltage, the induced EMF, I'll write it as induced voltage, by Faraday's law is the rate of change of magnetic flux. So it is delta of N secondary times magnetic flux divided by the time interval. The rate of change of this magnetic flux, by definition, is, well, it is Faraday's law is the Maxwell equation. The minus sign, they just ask about magnitude, so you can forget the minus sign in your answer. In other words, since the expression in the brackets is exactly mutual inductance times current in the primary, like this, well, the current in the primary doesn't change because it is the current generated by some generator from the grid. So this doesn't change. The only change is the coefficient of mutual inductance. So you have this expression here is just the change of the coefficient of mutual inductance. The current doesn't change, and the time interval also doesn't change. So the change of coefficient of mutual inductance per unit time, so you say you have doubled, increases mutual inductance by a factor of 2. The new value of the induced current is going to be, so delta M is 2 times M I delta T. In other words, the induced voltage is going to double. So the induced voltage, V induced, is going to be V induced is going to be 2 times V induced initial. Or initial, okay, initial. So you double the coefficient of mutual inductance, you're going to double the voltage. So they say originally the induced voltage in the secondary is 0.49. When you double the coefficient of mutual inductance, you're going to double this voltage. So it is going to be 0.98. 0.98 volts is going to be when you have material like a handgun between the two coils, right? Here is the handgun. Yes. Okay. Any remarks? So it is a lot of talking, but the answer is simple. And I gave this problem because metal detectors are everywhere nowadays. Remarks and questions? If not, let's go to problem number 16, a transformer. And here is a good diagram showing what the transformer is. Right, so you have primary coil, which is energized, and secondary coil, which is not energized, but a voltage and current is induced in the secondary coil. And this iron core makes sure that all the magnetic flux that is generated in the primary is moved to the secondary coil practically with almost no losses. Almost no losses. Just the ferromagnetic materials attract those magnetic field lines, and almost no magnetic field lines go outside. So you have a transformer with 2 coils, of course. The primary is 20, and the secondary is 22 turns. In other words, this is a step-up transformer. It's going to increase the voltage. So the peak voltage in the secondary, so across the resistor, is given. What is the peak EMF of the generator? The peak voltage of the generator. Well, look. The basic equation that describes the number of turns and the voltages and the currents look like this. Number of turns in the, let's say, in the primary divided by number of turns in the secondary coil is the same. So this ratio is exactly the same as the voltages in the primary and the voltage in the secondary coil. But we don't need it for this problem, but you have to know that it is the opposite fraction for the currents. In other words, the current in the secondary is like this. Current in the secondary divided by the current in the primary. We don't need it now, but you may need it in some other problem. We may actually use it if we want, but for the moment, look what happens. You have, for my version, the number of turns in the primary is 20. The number of turns in the secondary is 22. Which means that you have, well, you can practically analytical expression that gives you the answer is this one. But for our case, I'm going to have voltage in the primary divided by the voltage in the secondary is equal to 20 divided by 22. So they say that the voltage across the resistor, which is the same thing as the voltage in the secondary. So the voltage in the secondary, peak voltage in the secondary is given. In other words, the peak voltage in the primary, I'll use subscript 0 for amplitude, peak voltage, is going to be peak voltage in the secondary. So subscript 0 means amplitude, peak voltage, times 20 divided by 22. So this allows me to find, and this should be the answer. What is the peak EMF in the generator? So it should be whatever voltage they have given there times this problem. To make it trickier, this problem may ask what is the RMS voltage in the primary. So in that case, the RMS voltage in the primary would be whatever you get. So V primary RMS value is going to be V primary amplitude value divided by square root of 2. Right, to remember the connection between RMS values and amplitude values, peak values. But this is the answer for my version of the question. Any remarks? Another question that you can ask here would be, what is the current in the secondary, let's say, or in the primary? And you find that current directly using also this part of the equation for transformers. Let's see questions and remarks. It's very quiet today. Even people on Zoom? No?
Yeah, nothing.
Nothing. Wow. Okay, in that case, let's go to chapter 20. So this is 22, chapter 23. So last time I started the chapter by trying to justify the time and effort that is needed to describe the workings of circuits that include capacitor and inductor. And we said this is important because based on a circuit that includes capacitor and inductor, you can build a radio receiver, a radio transmitter, a TV set, and everything else. And you're going to see that even though the description of those circuits is involved, I'll make it to follow the same pattern for different circuits. So once you figure out how it works for the simplest circuit, you can reproduce the behavior of the more complex circuits. So last time we started with a circuit that contains only a resistor and AC voltage. So the AC voltage at any moment of time is some amplitude V naught multiplied by sine of 2 pi ft. So 2 pi f is exactly what we call angular frequency, angular velocity, angular frequency omega. So this is why this 2 pi is there in order to have the expression under the sign as omega times t. And we said that for this simple circuit, the instantaneous value of the voltage at any moment of time, so V at certain moment of time t, looks like a standard sine function. Sine function that is just the way we know it. So this is the zero. The amplitude is here, V naught. Negative V naught is here. And you have 60 hertz, 60 ups and downs per second for the case of the AC voltage from the grid. We said that because of Ohm's law, the current at any moment of time is just the voltage divided by the resistance. In other words, it is V naught divided by resistance R times sine of 2 pi of t. So usually V naught divided by R is what we call I naught. And therefore, you can draw in a similar way, you can draw the current in at any moment of time. The current is going to be like this. It's going to be exactly in sync with the voltage. Exactly in sync with the voltage. In other words, if you start changing the frequency from 60 to a different frequency, 100 hertz, the resistance is going to be constant. The resistance is constant with respect to changing a frequency. You change the frequency as much as you want, the resistance is 10 ohms or whatever number of ohms you have connected. And therefore, you represent that constant resistance as a function of the frequency as constant horizontal line. Frequency 0 to frequency million hertz, you're having the same resistance. And now the tricky part is the phasor representation of this voltage and current. And the phasor representation looks like this. At certain moment of time, t, you're going to represent the voltage with a phasor like this. You take the phasor, which is just like a vector, with the maximum value, V naught. So the length of this vector has to be V naught. And this angle right here is 2 pi ft. Sine, so V naught times sine is going to be this. So the instantaneous value of the voltage is going to be here, V of t. This is the instantaneous value of the voltage at a certain moment of time, t. At the next moment of time, this phasor is going to rotate around its end, around its tail. So at next moment of time, this phasor is going to be here, and therefore the instantaneous value of the voltage is going to be this, and so on and so forth. The current differs from the voltage by just a factor of resistance, so the current is right here. Another phasor that is on top of the first phasor, but it has different length because it is divided by the value of the resistance. So this is the phasor representation of this variable voltage and variable current, variable in time. So notice that the power that is consumed by this resistor is just the product of voltage, right? The average power consumed in your resistor is, or not average, let's make it instantaneous value. is going to be the product of the instantaneous value of the voltage times the instantaneous value of the current, whatever they have. So in other words, at certain moment of time, this is the voltage. At that moment of time, this is the current. And their product gives you how many watts this resistor is consuming at that instant, at that moment. So it's going to be some positive time. Positive is some positive number of watts is consumed. When the voltage and the current are in negative direction, like at this moment of time, right? Negative voltage, negative current. Negative times negative gives you positive consumption. Positive power, again, is consumed. In other words, all the time, this resistor consumes energy at a rate given by the product of voltage times. You can draw actually that consumption, but I'm not going to because we're running out of space. Now, let's repeat the same procedure for another simple circuit. So a simple circuit now that contains a capacitor only, capacitor with capacitance C connected again to AC voltage supply that has exactly the same time dependence, V naught times sine of 2 pi f t. Well, let's draw again the time dependence. So you're going to have a standard sine function for the voltage as a function of time. The maximum value of the voltage, of course, is V naught. Like this. However, unlike the previous circuit, you're going to see something unexpected for the current that is flowing in this circuit. So the current that is flowing in this circuit is going to, look what is happening. Let's say at moment of time t equal to 0. When t is equal to 0, sine of 0 is 0, the voltage is 0. 0 voltage, the capacitor is not charged. But look what happens. When the voltage starts increasing at the next moment of time, so you start here, at the next moment of time, the voltage starts increasing. And this voltage is going to drive charges and going to charge the capacitor very easily. A little bit later moment of time, when the voltage increases even further, well, the charges that are flowing, charging the capacitor, are going to have more difficult time because there are already charges on the plate of the capacitor, and those charges are repelling the newcomers, the new charges. So even though you are increasing the voltage, the flow of charges slows down. It is not as fast as it originally was. And as a result, at the initial moment of time, when the voltage is close to 0, you're going to have high current. And after that, the current is going to slow down just because the charges that are already on the capacitor are preventing, they're trying to stop the newcomers, the new charges. And you're going to have dependence like this. So the fastest change is happening, the fastest change of voltage is happening when you go to 0 voltage. And when you go to 0 voltage, you're going to have highest current, in this case in opposite direction, and so on. So in general, when the voltage has an extreme value, maximum or a minimum, you're going to have zero current in your circuit, or close to zero. And when the voltage goes to zero, you're going to have the maximum value of the current because no charges are present on the capacitor, and new charges are welcome to come with no resistance, no repulsion. So you're going to have practically similar to the sine curve. So let me try to draw it. You're going to have a curve similar to the sine function curve. But it is similar, but it is shifted with respect to the sine function. It is shifted. So look, here is the current. Well, the corresponding part of the voltage curve is right here. So we say that the current leads the voltage. So the current I leads the voltage in the circuit. By how much? By this time interval. This time interval is a quarter of a cycle. The whole cycle is this. So a quarter of a cycle, or 90 degrees. If you say that the whole cycle here is 360, a quarter of a cycle, 90 degrees, is the lead of the current. In other words, on the phasor diagram, the phasor diagram, here is the voltage and the current. So this voltage, this angle of the phasor is 2 pi ft, rotates this way. But the current itself is already 90 degrees ahead of this rotation. The phasor representing the current has already rotated 90 degrees more than, so it is leading the current by this 90 degree rotation. Also, look, a capacitor is two metal plates separated by air, separated by insulator, air or some other insulator. Therefore, strictly speaking, no charges can cross the gap of this capacitor, strictly speaking. So if you, instead of a AC voltage, if you put a battery with DC voltage, what's going to happen is the capacitor is going to get charged in 1 nanosecond or so, and after that, any motion of charges is going to stop. Any current is going to stop. In other words, the capacitor prevents DC voltages from creating any current. The capacitor DC voltage is voltage with frequency 0. No change, 0 frequency. So the capacitor stops signals that have 0 frequency, but the capacitor easily allows higher frequency signals, because higher frequency means, well, you charge, discharge, you charge, discharge. So constantly current, AC current is constantly going to be moving if you have AC voltage. So the capacitor has this interesting property. It resists signals that have 0 frequency or low frequency, and allows perfectly well high frequency. In other words, you can say that the resistance of the capacitor changes with frequency. So here is the frequency, on the horizontal axis. And the resistance of the capacitor is called capacitive reactance. Or sometimes you can call it capacitive resistance. And it is denoted with XC, capacitive resistance, capacitive reactance. And the resistance is very high at zero frequency. In other words, you're here, zero frequency, you're very high. And at high frequency, the resistance is very low. In other words, it behaves like this. And indeed, experimentally, the capacitive resistance is 1 divided by 2 pi frequency times the capacitance of the capacitor. High frequency means large denominator. 1 divided by a large number gives you a small resistance. Small frequency, 1 divided by some small number gives you a large resistance. So, of course, capacitive reactance is defined as the value of the RMS value of the current, of the voltage divided by the RMS value of the current. And it has dimensions of ohms, just like ordinary resistance. And we have 4 more minutes. The last simple circuit that we have to describe is a circuit that contains a single inductor with inductance L connected to AC power supply, like this. V equal to V naught times sum of 2 pi t. Oh, by the way, before I go to the inductance, notice how much, let's try to figure out how much power is consumed by the capacitor, a single capacitor. Look, the power consumed at any moment is again product of voltage at that moment times the current at that moment. But look what happens. At the first quarter of a cycle, you're here, you have positive voltage and you have positive current. Positive times positive is going to give you positive power consumed in the capacitor. So the capacitor is taking power, taking energy from the generator, from the grid. However, in the next quarter of a cycle, voltage is still positive. However, the current is negative. So positive times negative is going to give you a negative power consumed by the capacitor. In other words, the capacitor returns the energy back to Idaho power in that quarter of a cycle. At the next quarter, both of them become negative. Both voltage and current are negative. Again, negative times negative gives you positive, and you consume energy, and so on. So half of the time, the capacitor takes energy from the grid, but the other half of the time, it returns back that energy. On average, energy consumption of the capacitor is 0 on average. So P average is 0 for this capacitor. Well, if you don't consume energy, you don't do much. You're just taking a few joules, returning back those joules in the next quarter of a cycle. Yes?
So that the equation is instantaneous power then, right?
So the instantaneous value of the power consumed, half of the time is positive, half of the time is negative, and on average, the average value of the consumed power is going to be 0.
And then for V and I, they would be instantaneous as well, right?
So those are instantaneous values, while the average values are going to be 0 of average over time. Okay, so we're kind of running out of time. But the next circuit that we're going to repeat the same pattern is a circuit that contains a single inductor. And look what is going to be the situation with this simple circuit. The voltage created by the generator is still the same. So it still looks like a sine function. However, notice that the sine function changes very fast when it goes close to 0 and changes very slowly when it is going through the maximum or through the minimum. As a result of that, you are going to have, when you have fast change, you're going to have large induced voltage in the inductor, large induced current, and because of the negative algebraic sign, right? So the induced voltage and therefore the induced current is proportional to the rate of change of magnetic flux with minus algebraic sign. So this negative algebraic sign is telling you that, well, you're increasing the voltage, but the current is going to be negative. The rate of change of the voltage is very high. And as a result, you're going to have high current, induced current in this inductor, but it is going to be, because of this negative sign, it is going to be negative. After that, the rate of change of voltage is going to be small when you are at the maximum, and therefore small rate of change means zero current, no change, no induced current. So you're going to have a similar situation like before with the capacitor. Again, the current in your circuit is going to be out of sync with the voltage, and it is going to look like this. So you're going to have going to the maximum, going through 0 here, and going through a maximum here, and 0 here, and so on. Maximum here. In other words, you're going like this. And if you look here at this segment, and if you go to negative times for the sine function, it is like this. So this segment looks like this segment of the voltage. And we say that the current lags behind. So the current lags behind the voltage by a quarter of a cycle. The current lags behind the voltage by a quarter of a cycle. So next time we're going to do the phasor diagram. So here is the voltage, and the current is lagging behind. The current I lags behind. And we're going to say that you have inductive reactance that is going to be high, inductive resistance high at high frequency, and it can be shown it to be 2 pi FL. In other words, the inductive resistance with frequency increases proportionally to the inductive resistance. So we're going to talk a little bit more about the inductor on Friday. And on Friday, we're going to consider the last circuit, a circuit that contains a resistor and a capacitor and inductor connected in series. And this is the circuit that is going to be sensitive to particular frequency, and you can make a radio receiver using only that circuit. So, or TV receiver. So this is coming for Friday. Don't forget, homework assignment is due tomorrow night. And see you on Friday.